Hi all, and welcome to the Medical AI Lab group session. Today I'm delighted that we have Vignav Ramesh presenting to us on a paper called Language Meets Vision Transformer in Medical Image Segmentation. So without further ado, Vignav, take it away.
Let me go ahead and share my screen. Can you see this? Great. Okay. So hi, everyone. Today I'll be giving a presentation on the paper LViT, Language Meets Vision Transformer in Medical Image Segmentation. So it's probably best to begin with a quick background on a semi-supervised learning technique called pseudo-labeling, which is really essential to the LViT paper. So generally, large amounts of labeled data are required to train more capable ML models. However, pseudo-labeling has largely alleviated this problem. Given a small labeled dataset and a large unlabeled dataset as input, the pseudo-labeling task is one of induction. So that is, the goal is to obtain supervision signals from the labeled dataset in order to generate predicted labels, which are called pseudo-labels, for the unlabeled dataset. So this is a four-step process. First, a model is trained supervisedly on the labeled dataset. Second, that model, via inference, predicts labels for the unlabeled data, thereby creating our pseudo-labeled dataset. Third, the pseudo-labels are treated as target labels to calculate loss, and then backpropagation occurs. And finally, fourth, we repeat, allowing us to iteratively generate higher quality pseudo-labels and thus train more accurate models. So the LViT paper applies the concept of pseudo-labeling to the medical image segmentation task. So as we all know, medical image segmentation is one of the most critical tasks in medical image analysis. And currently in clinical practice, accurate segmentation results are often achieved either manually or semi-automatically. However, extracting desired objects accurately, especially when the target organ to be extracted is of really high complexity in terms of the tissue structures and things like that, is extremely challenging. So recent research has shown that deep learning methods are a promising approach for automatic medical image segmentation, because the knowledge of experts can be learned and extracted programmatically. The majority of deep learning segmentation methods are structured in one of three ways. So first, as one shared encoder followed by two separate decoders. Second, as two separate encoders followed by one shared decoder. And third, as two separate encoders followed by a modality interaction model. But the problem with this is these deep learning models fall victim to two inherent issues concerning the creation of high quality medical image datasets, which are the difficulty in obtaining high quality images and the prohibitively high cost of data annotation. Since these issues make it challenging to improve the quantity and quality of medical images themselves, the idea of the LViT paper is to use complementary and easy to access text information to make up for the quality defects of medical images. So according to this paper, we can turn our attention to written medical notes that accompany medical images. Text data of medical records are usually generated for each patient. So in the majority of cases, no extra cost is needed to access the text data associated with image datasets. The medical text record data and the image data are naturally complementary to each other. So the text information can compensate for the quality deficiency in the medical image data. And moreover, given the prevalence of semi-supervised learning, given the difficulty of obtaining expert segmentation annotations, which is especially true for new diseases like COVID-19, medical text can also be used to improve the quality of pseudo-labels used in semi-supervised learning frameworks. So to summarize, this paper addresses two key challenges. First, how to improve segmentation performance using existing image text information, which is solved by the proposed LViT model. And second, how to make full use of text information to guarantee pseudo-label quality in semi-supervised settings, which is solved by the Exponential Pseudo-label iteration mechanism, or EPI. And we'll go ahead and discuss both LViT and EPI. But before that, we can quickly go through some related work. So semantic segmentation is often cast as a repeated pixel-level image classification task. So many image classification networks have been extended to implement semantic segmentation, and FCN was commonly considered the first semantic segmentation network for pixel-wise prediction. UNet and UNet++, which is simply a UNet model with improved skip connections, are often regarded as pioneers in medical image segmentation. However, all of these methods are extremely sensitive to the quantity and quality of training data, which results in limited generalization performance. So therefore, some approaches have explored the application of semi-supervised learning to medical image segmentation, and LViT is one of them. But I guess for prior art, contrastive language image pre-training, or CLIP, is a big one, which uses contrastive learning to learn universal representations from scratch And note that CLIP harnesses multiple modalities, basically image-text pairs, for more effective learning. And inspired by CLIP, a few semantic segmentation models using textual information have been released. Notable models involve contrastive losses between text and image embeddings, as well as cross-attention modules that inject textual information into image-based models. The key difference between LViT and prior art is that LViT does not use a text encoder on explicitly aligned images and texts. It only uses text embeddings without the additional encoder to achieve state-of-the-art performance. So as shown in the figure, LViT is a double U structure consisting of a U-shaped CNN branch and a U-shaped transformer branch. The CNN branch acts as the source of information input, so it serves as a segmentation head to output the prediction mask. The VIT branch is used to merge image and text information. It exploits the ability of transformers to process cross-modality information. A text report corresponding to the given image is vectorized with BERT, and then the embedding is merged with the image vector and sent to the VIT branch for processing. The fused joint text image embedding is then passed back to the U-shaped CNN branch at each layer for the final segmentation prediction. In addition, a pixel level attention module, or PLAM, is placed at each skip connection of the U-shaped CNN branch. And with PLAM, LVIT is able to retain as much local feature information of the image as possible. So we can go into the U-shaped CNN branch first. As shown in the figure, the U-shaped CNN branch is used to receive the image information and act as a segmentation head to output the prediction mask. So convolutional, batch norm, or BN, and ReLU activation layers compose each CNN module. Image features are downsampled between each down CNN module using the max pool layer and upsampled via concatenation between each up CNN module. So the specific process of each CNN module is given by these equations, where a Y sub down CNN I represents the input of the ith down CNN module, which becomes Y sub down CNN I plus 1 after downsampling the ith down CNN module via max pooling. A CNN VIT interaction module is also designed to align the features from the VIT with those of the CNN. And here, by align, what we mean is really make the features the same size. And as you can see in the interaction module figure, the VIT features are reshaped and upsampled and then connected with the CNN features via the add operation to construct CNN VIT interaction features that further integrate the textual and visual information. Next, we have the U-shaped VIT branch, which is designed for merging image features and text features. As shown in the figure, the first down VIT module receives the text feature input from BERT and the image feature input from the first down CNN module. The specific cross-modal feature merging operation performed by the first layer down VIT module is expressed in these equations. So here, X sub image I represents the image features from down CNN, and X sub text represents the text features. Patch embedding is the process of prepending textual information to a sequence of embedded image patches. And it's used here to help Y sub down CNN I form the image embedding X sub image I. So VIT represents the transformer encoder, and it consists of the multi-headed self-attention, or MHSA layer, and a multi-layer perceptron, or MLP layer. LN represents the normalization layer, and the CTBN block consists of the convolutional layer, batch norm layer, and ReLU activation layer for aligning the feature dimensions of X sub image 1 and X sub text. So all of these equations correspond to this first down VIT module that directly gets the input from BERT. But the subsequent down VIT modules for layers 2, 3, and 4 are much simpler. Given both the feature from the upper down VIT module and the feature from the down CNN module of the corresponding layer, this module adds the two features and then passes them through the VIT as shown in the equation. The output features are then transferred back to the CNN VIT interaction module through the upward layers of the VIT branch. And finally, we have the pixel level attention module, or PLAM. PLAM is designed to preserve the local features of the image while also further merging semantic features in text. So as seen in the figure, each PLAM module takes two items as input, a down CNN feature and the up VIT feature of the same layer. It uses parallel branches for global average pooling, or GAP, and global max pooling, or GMP. Concat and add operations are also incorporated. So the add operation helps merge the corresponding channel features with similar semantics, while the concat operation can integrate the feature information more intuitively and help preserve the original features of each modality, image and text. After concatenating the feature information, an MLP layer and multiplication operation are used to help align the feature size, as shown in the bottom right equation. So as you can see in the middle image, In the CNN branch, PLAM is incorporated into the skip connections at each layer of the CNN branch. So now, if you recall from earlier in the presentation, there are two key challenges that this paper addresses: how to improve segmentation performance using existing image text information, and how to make full use of text information to guarantee the quality of pseudo-labels. We just discussed LViT, the solution to challenge number 1, but challenge number 2, which takes us into a semi-supervised setting, is solved by the exponential pseudo-label iteration mechanism, or EPI. So now we can dig into how EPI really works. In EPI, the pseudo-label is iteratively updated using the idea of EMA, or exponential moving averages. So for a quick definition, a moving average is a statistical tool used to determine the direction of a trend. So it basically aggregates a subset of data points over a given time interval and then takes the average of those points. And moving averages are called moving because they are calculated repeatedly as time passes. Now, the difference between a moving average and an EMA is that EMAs are moving averages that apply greater weight to more recent data points. So we can see this process in the equation where P of t minus 1, which is an n-dimensional vector representing the model prediction at the t minus 1 time step, and n is the number of category classes. Beta is the momentum parameter set to 0.99. So if you recall the status quo pseudo-labeling process, first, a model is trained supervisedly on the labeled data set. Second, that model is used to predict labels for the unlabeled data. Third, the pseudo-labels are treated as target labels to calculate loss and perform backprop. And fourth, we repeat. So step 3 involves treating the pseudo-labels generated in step 2 as targets in the next iteration. And this leads us to the key benefit provided by EPI. Because of the periodic EMA updates, predicted labels aren't simply used as next generation targets. And this helps avoid sharp deterioration in pseudo-label quality. So the authors of the paper provide this proof, which shows what that statement means from a mathematical standpoint. So the basic assumption for the EPI algorithm is that the model weights will dither around the actual optimum in the last n generations or iterations. And therefore, the pseudo-label predicted by the model will also dither around the actual mask in the last n generations. So we can start with equation 1, the equation for EMA, and then expand P of t around t to get equation 2. In particular, we can let n equals 1 over 1 minus beta, and then we can let beta to the nth power equal beta to the power of 1 over 1 minus beta, which approximately equals 1 over e. And what this tells us is that for the first 1 over 1 minus beta generations, P of t decays to a weighted average of 1 over e. And then if we introduce an adjustment gradient g of t minus 1 for the predicted label P of t minus 1, we get equation 3. Finally, at our final time step t equals n, given the assumption that the first two pseudo-labels, the labels at time steps 0 and 1 are approximately equal, we get the final equation, which can be algebraically manipulated to yield this equation for P of t. And the key part of this slide is the right-hand expression in this final equation includes this weight coefficient, 1 minus beta to the n minus I power, for the gradient descent step of the ith iteration. 1 minus beta to the n minus I power will decrease as I increases. And that means that the change in the pseudo-label will be minimized and we'll finally end up with a stabilized pseudo-label with high confidence. So basically from the slide, the key part is seeing this weight coefficient in blue. Finally, to further utilize the text information to guide pseudo-label generation, the authors present the language vision or LV loss function. So as shown in the top equation to the right, text sim is the cosine similarity between two texts where x sub text P denotes the text corresponding to the pseudo-label and x sub text C denotes the text corresponding to a reference contrastive label that's used for evaluation. According to text sim, a contrastive text with the highest similarity to the pseudo-label is selected for evaluation. Then LV loss maximizes the contrastive similarity image sim between the pseudo-label and the contrastive label segmentation masks. So in this way, LV loss is a simple contrastive image loss, but it injects textual information into the setup of the pseudo-label and ground truth image pairs. So now that we've covered the methodology behind LViT and EPI, we can move on to experiments. So the two data sets used in this experiment to evaluate model performance are MONUSEG and the Cutter-Tampier COVID-19 dataset, or CUDA-COVID-19. In addition, the authors extended each of these datasets to include text for training the vision language model. So the loss functions used are shown in the two equations on the slide, where L supervised is the mean of dice and cross entropy loss, while L unsupervised, which evaluates the performance on unlabeled data, adds a weighted language vision loss, where alpha is set to 0.1. And the metrics used to evaluate segmentation performance are dice and MIOU. So LViT model performance was compared with several CNN and transformer-based segmentation models. And the numbers in parentheses denote the ratio of labels used. So for instance, LViT-T 1/4 indicates that a quarter of the train set labels were used. So this is a semi-supervised learning setting. And also the -T in LViT-T means the tiny version of LViT. And there's also LViT-S, -M, and -large that distinguish the small, medium, and large versions of LViT. And I'll discuss that in a bit. And the last thing to notice is the W in LViT-TW means without text information. So text reports aren't integrated in the model, and it's used for comparison to see how the text information improves performance. So experimental results on the CUDA COVID-19 dataset show that LViT-TW and LViT-T, so the tiny version and the tiny version without text, are able to achieve better performance than the previous state-of-the-art method with a smaller number of parameters and a lower computational cost. And it's also worth noting that LViT-T still outperforms the other SOTA methods, even when only a quarter of the training labels are used. And similarly, it can also be seen that LViT-T has a 2.54% higher dice score and a 4.05% better MIOU score than LViT-TW. And this also indicates that introducing text information improves model performance effectively. A similar trend is observed for the MonUSEG dataset on the right-hand side of the table. So now this figure shows the qualitative results of LViT and 4 other baseline models. So we see that LViT Tiny has excellent semantic segmentation capabilities. So the red boxes on the images show that UNet++, MED-T, GTUNet, and TransUNet, which are the 4 baselines, all have more severe missegmentation than LViT. And this shows that the introduction of text information in the LViT learning mechanism better guides the training of the model and leads to more accurate segmentation. So now, I guess the last thing to cover is a series of ablation experiments were also used to verify the performance of the LViT model. So in the first study, the authors explored the effectiveness of improvements from four perspectives: down VIT, up VIT, PLAM, and text. All 4 components are effective based on the results shown in this table, where the performance improvement brought by adding text information is most obvious. And relevant ablation experiments are also performed to address the authors' proposed innovations in semi-supervision. So effectiveness of 3 perspectives, EPI, text information, and LV loss are explored. And from the experimental results, it can be seen that all 3 improve performance. And it's especially noticeable that with the EPI mechanism, the semi-supervised performance of LViT is guaranteed to be comparable to the fully supervised performance of UNet, which is a huge accomplishment. So the authors also conducted ablation experiments for model sizes, and 4 different model sizes, each run with and without text information, were used. So this is where we see the tiny, small, medium, and large versions of LViT that I discussed earlier. And the differences between these different versions of LViT are in the number of transformer layers in the down VIT module and up VIT modules, where LViT tiny has only 1 transformer layer per VIT module, LViT small has 4 layers, LViT medium has 6, and LViT large has 12. So as shown in the table, increasing model size does not lead to performance improvement on the CUDA COVID-19 dataset. Model performance is further limited when model size increases to LViT-LW, which the authors think could be due to overfitting. But in contrast, there is a positive correlation between model performance and model size on the MonUSEG dataset. And ablation experiments were also conducted around 2 aspects of the hyperparameters, batch size and learning rate. So from the table, we can see that LViT is optimal for a batch size of 24 and a learning rate of 3 × 10⁻⁴ on the CUDA COVID-19 dataset. And in contrast, LViT is optimal for batch size 4 and learning rate 10⁻³ on the MonUSEG dataset. And I guess one key thing to note from this slide is that the impact of hyperparameters on model performance is more considerable than that of model size. So the final experiment described in this paper is an interpretability study performed on the CUDA COVID-19 dataset to explore whether the LViT network can notice lesion regions and whether the introduction of text information enhances attention to lesion regions. GradCam is used to compare activation maps for regions of attention. And the top figure, which indicates interpretability by model, shows that the 4 baseline models all have different degrees of misactivation regions. So for example, in the case of total lung infection, this only activates half of the lung region in other methods. But in contrast, by introducing text information in LViT, more regions are activated and the edge profile of the activated regions of interest are more consistent with the ground truth. Therefore, the localization of lesion regions are better learned by introducing text embeddings, which is a key finding of the paper. In addition, experiments were conducted to explore how the introduction of text information specifically helps activate regions. So if we look at the bottom figure, we see activation mappings were performed for the down CNN 1, 2, 3, and 4 layers, and down VIT1, as shown in the bottom figure, where the number just denotes the layer. So down VIT1 is the first down layer in the down VIT branch. And the difference in activation regions between down VIT1 and down CNN1 can be explained by the fact that text information is given to the model through down VIT1. And the CAM output of LVIT-TW and LVIT-T shows the final activation difference caused by text information. And the difference between these saliency maps indicates that text information effectively helps locate lesion regions in the lung. Future work for the paper will involve extending LVIT to conduct experiments on 3D medical data to verify the model's generalizability, because right now, LVIT only has experiments on 2D medical data for 2D segmentation. And yeah, that's all I have. Thank you for listening.
Thanks, Vignav. Thanks for the wonderful presentation.